I'm Mark Kavanaugh for Kevy Coaches, and today I'm going to coach you up on torque. It's force, but with a twist. All right, so today we're going to talk about torque, which is actually a force with a twist. We have a force that is applied to an object at a distance from a locked point, which we call a pivot point, and that causes the object to rotate or to twist. So we have an object which is locked in at the pivot point as seen here. And if we apply a force at some distance away from that pivot point, then what's going to happen to this object is it's going to twist or rotate. So an example of this that you use every day would be opening a door. So consider a door in which the hinge is connected to the wall. And we have a force that's applied. Maybe it's applied at some angle theta in relationship to the door and applied at some distance r from the pivot point. So with the force acting at an angle, this will still cause the door to rotate, although the force is at an angle is not going to give us the optimal torque. So even though the force is acting at an angle, it's still going to cause it to twist. It's just not going to be the maximum amount of torque. Perpendicular forces apply the maximum amount of torque. So in this case, the force being applied is going to cause a counterclockwise rotation, which is we're going to use in this video abbreviation CCM, and a counterclockwise is considered the positive direction. So if we give the values for F and R and theta, the torque can be calculated using the equation. Torque, which is the Greek letter tau, is equal to the force that is applied in newtons and the distance measured in meters. This is also called the moment arm. And theta is the angle between F and R. It's the acute angle between F and R, so the angle between 0 and 90. So if the force was applied up and to the left, it would still be the same angle measurement at between 0 and 90. So let's simplify the torque equation with a perpendicular force to the door. So if a force is applied perpendicular, we know that theta is 90, and torque is equal to force times distance times sine of theta. Well, if sine of theta is going to be sine of 90, and sine of 90 is 1, so that means torque is equal to force times the distance. So here's a question for you. Why is the doorknob far from the hinges of a door? Why isn't it in the middle of the door, which would be symmetrical and would look kind of fancier and nicer? Why isn't it closer to the hinges? So force being applied at some distance, we know that that's causing a torque. So if we consider the force acting perpendicular, torque equaling force times distance, if we apply the force at half the distance from the pivot point, then that means in order to apply the same torque, we would need to double the value of the force that's applied. So why is the doorknob far from the hinges? Well, the reason is we can apply a force at the edge. It decreases the amount of force required to open the door. If the side to the door was closer to the hinge, the torque would be smaller. To exert equal torque in the middle, you'd have to apply a much greater force. And you can try this. Try pushing a door open from closer to the hinges than from the outside, and you'll see it's going to take much more force to cause it to rotate with the same angular velocity. So what are the units for torque? So the SI units for torque, if we're multiplying force times distance, newtons and meters, that gives us a unit of meter newtons or newton meters. Now we also know that a joule is a newton meter. So can we substitute joule? Is torque really just an energy? And the answer is no. A joule is a measurement of energy, which is a scalar quantity, which direction does not matter. But torque is a vector quantity in which direction of the torque does matter because it's a force vector applied at some distance. So let's look at an example problem where we have an object in static equilibrium, meaning torque and forces are balanced. So static equilibrium must satisfy two conditions. All forces in the x and y direction are balanced, which we did back in Newton's first law. And all torques in the counterclockwise and clockwise directions are also balanced, Newton's first law for torques. And both must be proven to show an object is in static equilibrium, or if we know an object is in static equilibrium, we could use both to find values of multiple unknown forces. So here are the steps to solving a problem in static equilibrium. So the first thing you're going to do is draw a force diagram of all relevant forces. A force diagram, we've been drawing free body diagrams where we take an object and shrink it to a single point, which we're not going to do. We're going to draw all forces acting on the object where they actually act on the object. So we would draw a picture to represent the actual object and draw forces not all coming from that same point. Then we're going to decide the location of a pivot point. This is the point where we're going to use this to find distances for each force that's applied. And it doesn't matter where we choose the pivot point. If we know an object is in static equilibrium, all torques around that specific pivot point are going to be balanced. So we can pick it anywhere along there. The best location to pick it is usually at one of the unknown forces if we have multiple unknown forces. Step 3 is to write the Newton's first law equation for torques and determine the direction either clockwise or counterclockwise for each individual torques. And the equation we're going to use is the sum of torques in the counterclockwise equals the sum of torques in the clockwise direction. Step 4 is to find the distance from the chosen pivot point to each force. The reason this is important is we're turning forces into torques by multiplying the force times the distance from our chosen pivot point. And remember, the pivot point can be chosen anywhere, but the location needs to be usually at one of the unknown forces. Then we're going to solve the torque equation for an unknown force, value substituting in the torque equation. Then we'll write the Newton's first law equation for the x direction and the y direction in terms of forces. So the up forces equal the down forces or the right forces equal the left forces. And our last step is to solve the equation for the remaining unknown force. So let's look at an example problem. We have a 25 kilogram table. That table's 2 meters long and it sits at rest on the floor. Each leg is 0.25 meters from the end of the table, and we place a 3 kilogram physics textbook 0.5 meters from the left edge. So we know that this is in static equilibrium because it's not rotating. Our question is to find the value of the force on each leg. So step 1 is to draw a force diagram for the table. So we're not going to draw on the diagram, so we're going to just draw a line to represent the table, and then we're going to go through the forces that are acting on the table. One force that acts on the table was the gravitational force. Now, because we're drawing it from specific spots, we have to draw the gravitational force from the table's center of mass, which is going to be the center of the table. So we have the gravitational force on the table. Now we also have a gravitational force from the textbook that's sitting on the table, and we're going to draw that in a location that where the physics textbook center of mass is pointing. Then we have the force of the left leg and the force of the right leg. And notice that the left leg is drawn a little bit longer than the force of the right leg. Why is that? Well, the mass of the table and book combined is more shifted towards the left leg, so that's going to have to exert more force to support the table than the right leg. So now that we have our force diagram, we're going to choose a location for the pivot point. And we can choose the pivot point again anywhere on here because we know that the table's in static equilibrium. It's not moving and it's not rotating. So we're going to pick one of our forces that are unknown, either the left leg or the right leg. It doesn't matter which one we pick, but for this example, I'm going to choose the pivot point to be from the left leg of the table. So now we're going to write a Newton's first law equation for torques. The sum of the counterclockwise torques equals the sum of the clockwise torques. And remember, we're turning these forces on our force diagram into torques. So we're going to use the equation that torque is equal to force times distance. So now we need to figure out which direction do each of these forces apply a torque around our selected pivot point. Well, the force of gravity would pull down, which would cause the table to rotate clockwise. So we're going to put the force of gravity on the book times its distance on the clockwise side. And likewise, we have the force of gravity on the table pulling down. So that's going to cause a clockwise rotation as well. Now the right leg is going to cause a counterclockwise torque. So the force is going to be on the left side of our equation. So we'll turn that into a torque by multiplying by the distance. Now, just because forces point up and down does not mean that every up force applies a clockwise torque and each down force applies a counterclockwise torque. We could have two downward forces. If they're on opposite sides of the pivot point, they would cause opposite direction torques. So it's important to understand that you have to figure out which way the object would rotate based on the force, because two forces pointing in the same direction could cause a different direction torque. So now let's do step 4, finding the distance from each of the chosen pivot points. So we're going to find the first force, which is the closest to the pivot, which is the force of gravity on the book. We know it's 0.5 meters from the left edge of the table, but we're not finding the left edge of the table. It's from the left leg, which we're going to subtract these two numbers to get 0.25. Then we're going to find the distance to the force of gravity on the table. Well, we know that the force of gravity on the table comes from the center of mass. And the center of mass would be right in the middle of the table, which is 1 meter in the exact center of the table. But that's not the distance because we're still finding it from the left leg. So we're going to subtract those two numbers and find 0.75 meters is the distance from our pivot point. So now we're going to find the distance between the legs, and we know that the table is 2 meters long and each leg is 0.25 meters in. So what we're going to do is use these numbers and find the distance between the legs is 1.5 meters. So the distance between the right leg and our pivot point is 1.5 meters. Step 5 is to substitute into the torque equation, first solving for our unknown force. So we know that we're solving for the right leg, so we can divide each side by the distance that the right leg. Then we can substitute our numbers in. We've substituted mg for our force of gravity, the distances for each of our objects, and then we can solve for the force of the right leg and get 127.4 newtons. So that's how much force the right leg exerts on the table. So now to find the force that the left leg exerts, we can just use Newton's first law equation in the x and y direction. Well, we don't have any x direction forces, so we're only going to use the y direction forces. So we know that the sum of forces up equal the sum of forces down, and we can see that the left leg and right leg point up, and the gravitational forces on the book and table point down. Then we can solve this equation for the remaining unknown force, and we're looking for the left leg, so we're going to subtract the right leg to the other side, substituting mg for each of our forces of gravity. Then we can substitute our values in to find the force of the left leg, substituting the masses in 9.8 for g and 127.4 for the right leg, which we found using torques. So that means that the left leg is going to exert a force of 147 newtons. So let's check and make sure our answer makes sense. So the right leg exerts 127.4 and the left leg 147, which at the beginning we said, yes, the left leg is going to exert more force than the right leg because the textbook is shifted towards the left leg, so our answer does make sense. So let's recap this because there's a lot of information that we went through in that example. So remember, step 1 is to draw a force diagram of all relevant forces. So we draw a line to represent the table and the forces acting from the specific spots on the table. Then we decide the location of the pivot point. In this example, we chose the pivot point to be at the left leg. Then we are going to write our Newton's first law equation and determine the direction for each of the forces. So the clockwise torques were the gravitational force in the book in the table, and the counterclockwise torque was the right leg. Then we find the distances using the measurements that were given in the problem, and we find each of the distances from our chosen pivot point. Remember, it's not from a specific spot other than our pivot point. Then we're going to solve for our unknown force value, and we are going to find the value of the force of the right leg. Then, step 6, we write the Newton's first law equation for the x direction, so the up forces equal the down forces. And then step 7, we solve the equation for the remaining unknown force, substituting our numbers in, and we find the value of the force of the left leg was 147 newtons. And lastly, we just double check to make sure that those answers made sense with how our free body diagram was drawn. And we can see the left leg is 147 newtons and the right leg was 127.4, so our answer made sense. So this is an introduction to torque and static equilibrium problems. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below and subscribe to my channel, Happy Coaches, and follow me on Instagram and Twitter at Happy Coaches.